Hi everyone, hope you had a nice bank holiday weekend. We're back today with GCSE Physics, and today we're going to be carrying on the topic of space. So we're going to be talking about the expanding universe. As always, these sessions are 1 hour long and they will be recorded, so you can go and watch them on YouTube later. If you don't know me already, I'm Preshayla. I'm the physics tutor for the online school, and I study physics at Loughborough University, and it's my 4th year as a tutor. So what we're going to cover today is a recap of what we've done in space so far, as always, understand what keeps our planets where they are, so in terms of the forces that are needed to keep them where they are, understand the ways in which we use satellites to fit our daily needs, know what redshift is and how it is relevant to the universe, understand what emission spectra are and how we can use that to understand the composition of stars, and be able to discuss how we know the universe is expanding. We'll go through some example questions and we'll have time for questions at the end. If you guys do have any questions along the way, please don't hesitate to ask, just put them in the chat or the Q&A and I will try to pick them up as I go along. But yeah, at the end as well, we will have time for questions. Okay, so we're going to be talking about the expanding universe today, and the kind of topics in the title. The universe is expanding constantly, and we're going to work our way up to understanding why that is. But first, let's go over the facts that we remember from the last webinar, which was the formation of the solar system and the life cycle of a star. So I've got a little activity here for us to do, which is a word cloud. So if you could, please go to the website Slido. So it's sli.do, sli.do, and enter the event code 15979. So I'll put it on the chat as well. And I just want you guys to put some ideas of what kind of facts you remember, what ideas you remember from the last webinar, which was on Thursday, about the solar system and the life cycle of a star. So the link is that, and the code is 15979. So when you click on the website, you should have a option to enter the code. You can access it from your laptops or your smartphones, and when you do enter the room, just put your answers in. Okay, so what facts do you remember about our solar system, about the planets, about comets, asteroids, our galaxy? What facts do you remember about the life cycle of a star? What different types of star do we have? What happens after a supernova? How do we produce elements? How is iron produced? All those kind of facts I want in there. Cool, loads of great answers coming in. About fusion, some comets, Milky Way. Someone's even put their entire life cycle, which is great. Give you 2 more minutes to have a think about any more facts that you can think of. Okay, so these are the kind of words that we're getting in from your answers. You can see that fusion is a big one there, which is really great because fusion is really what makes a star stay burning. So stars are constantly fusing elements together to create new elements so that they can keep on giving off energy. And that's exactly what the sun does. So the sun is constantly burning and fusing hydrogen to create helium, which allows it to keep burning and allows that energy to keep being emitted. We've got giant in there, we've got gravitational attraction. So when we were talking about gravitational attraction, that's the kind of gravity forces acting on the outside of a star, and then the radiation from the inside being emitted out. And those two forces balance each other out, which is what allows the star, again, to stay in equilibrium and to keep burning. Other things that we have in there is iron. So we can see iron that's a really great one to put because that's talking about the production of elements. So stars burning create all the elements that we see on our Earth, but any elements that are heavier than iron require more energy to be produced. And therefore it needs a supernova to produce elements which are higher or heavier than iron. Okay, so that's really great, guys. I can see lots of you have put some really good answers in the chat there, in the poll, sorry. Okay, so let's move on with the content for today. So we need to talk about the force that keeps the planets where they are. So we know that planets are constantly orbiting the sun. We learned that last lesson when we were talking about the solar system. There are 8 planets which orbit the sun, Earth being one of them. Now the Earth has a very circular orbit, so a very regular circular orbit, but most other planets have a sort of elliptical orbit. Okay, so remember, elliptical is just this shape, which is kind of a squashed circle, so not quite circular. Yeah? Okay, so gravity acts on the planet. So we know that gravity acts between any two kind of objects with mass. So we are constantly feeling the effects of gravity because we have mass, and every object around us feels the effect of gravity, which is why everything that goes up must come down. And it's why everything that is kind of put on a table stays on a table. So we know that gravity acts between everything that has mass. And that's no different for the planet and the sun. So in the diagram here, you can see that the planet is attracted to the sun because of this gravitational attraction. So we can see that the planet has an inwards force of gravity. Okay, so this red arrow depicts the gravitational force. Now, because that is the only force acting on the planet, we call it a resultant force. Okay, so our gravitational force between the planet and the sun is the only force which acts on the planet, and therefore we call it a resultant force. Okay, so if we remember back to a few webinars ago, we were talking about resultant forces, and resultant forces are just, it's just a force that kind of makes it move. So it's overall force, it's net force. So it's got a really big pulling in one direction, but a small pulling in the other direction. The overall force is going to go where the biggest force is. And that's the same for the planet. The overall force, the resultant force, can only come from this gravitational force. Okay, so, okay, we have a resultant force acting on the planet. Now, there's another special word for this resultant force, and that's called a centripetal force. Okay, so we have this new key term, which is a centripetal force. Centripetal force. Now, centripetal force is a force which acts towards the center of a circle. So we can see that our gravitational force can also be known as a centripetal force because it acts towards the center of a circle. Okay, so the planet has a gravitational force towards the sun, and that kind of acts as our centripetal force. Now, the reason that it's called centripetal is because it acts towards the center of the circle. So center, century, center kind of match up. That's the way that I remember it. And the centripetal force is just this kind of new key term which we use to talk about the force on the planet. Now, another kind of key fact to do with centripetal force is that motion is perpendicular to force. So we can see that the planet is moving in this direction here, or this direction, and it's constantly changing direction. Right? So it goes round this orbit and it constantly changes direction. But what's important to know is that no matter where it is on the circle, no matter where it is in its orbit, its motion is always perpendicular to its force. Okay, which we can see in the diagram. The force is acting towards the center of the circle, our centripetal force, but its motion is going this way. Yeah, and therefore we can say that they are at right angles to each other. So another key fact is that motion is perpendicular to force. Okay, now we know that a planet orbiting the sun has a constant speed. Okay, so our Earth rotates around the sun with a constant speed. Now, okay, it's rotating around the sun with a constant speed, but it also constantly changes direction. So we can see that the planet is going this way, then it starts going off here, and so on. So we can see that it keeps changing direction constantly. Now, although the speed is the same, how fast they're going, the value is the same, the direction changes. Now, if we remember our definition of velocity, velocity is speed with direction. So although speed stays the same, direction is constantly changing, and therefore velocity constantly changes. Okay, so although we have a constant speed, we do not have a constant direction, and therefore the velocity constantly changes. Now, it's kind of weird to think about because we usually think about velocity as being the speed, and if the velocity changes, that means that the speed must be changing. But actually, no, here, the speed is staying the same, but the direction is the part that is changing. Okay, so we know that our planets are kept kind of where they are because of this idea of gravitational force and centripetal force. But what happens if a planet gets too close to the Earth? So it could be a planet, could be a star, satellite, comet, asteroid, any of those. If one of those gets too close to the Earth, then it will gradually lose speed. Okay, so you can see that if it's in this kind of black dashed orbit here, you can see this black dashed orbit here. If it's in that orbit, it's going at the correct speed and it won't spiral in. It'll be absolutely fine and it will stay in orbit forever. However, if it gets too close to the Earth, so if it comes in underneath this black orbit, it will gradually start to lose speed because of the gravitational forces from the Earth. So the gravitational forces from the Earth will start to attract this planet, this satellite, whatever it is, and start to kind of drag it down. Okay, so it starts to lose speed because of this thing that we call atmospheric drag. Okay, so it's starting to lose speed, and because it's starting to lose speed, it gradually spirals in. So if it is underneath this orbit, it's way too close to the Earth and it's going to start to slow down and gradually spiral in and eventually hit the Earth. Okay, so it's really important that we get our satellites at the correct speed, because if they're too slow, they'll spiral in and hit the Earth, and if they're too fast, they'll just ping off into space. So it's a very kind of accurate science, which means that if we don't get the right speed, then it could either fly off into space or fly into Earth, both of which would not be very helpful for us. So for a satellite to stay at this correct height, to stay in this black orbit, it needs to be going at a certain speed. Okay, if it wants to be slightly out here, if it wants to be slightly in here, the speed needs to change. So for a planet or a satellite to stay at a constant height above the Earth, it must go at a certain speed. Okay, so talking more about satellites then, the further we are away from the sun, the less the speed is needed for it to orbit. Okay, so if we're further and further out from the sun, the speed of the satellite can go slower. And the reason for this is because gravity is weaker the further and further away we get from the planet. Okay, so for an example, on our Earth, we know that gravity has a strength of 9.8. Yeah, G is 9.8. Now, okay, that's for the surface of the Earth. So at the surface of the Earth, G is 9.8. But when we get further and further out from the surface of the Earth, as we start to get further and further out, the gravitational force starts to weaken. Okay, so objects aren't as attracted to the Earth when they're further out. Okay, so we know that an orbit can go out from the Earth. And let's say this is the orbit. That's going to take longer because the circumference is bigger. Yeah, so if we look back to our Earth here, we see that we've got an orbit going around the Earth. And if we were to do an orbit that is slightly further out from the Earth, we can see that the circumference is bigger and therefore it would take longer at the same speed. Okay, so an orbit that is further out from a planet, from the Earth, takes longer. Now, the equation that we use for this is that time equals circumference over speed. And what it really means is that speed equals distance over time. But all they've done is replace distance with circumference. Okay, so they've replaced this distance with circumference. Now, we have a special sort of satellite called a geostationary satellite. Now, a geostationary satellite is a communication satellite which has the same period as the Earth. Okay, so it rotates around the Earth, it orbits the Earth with the same period. It goes as fast as the Earth does. And it travels in the same direction that the Earth does. And therefore, it stays at the same point on the Earth's surface. So it matches the speed of the Earth. And because it stays in one place on the Earth's surface, it can constantly observe and communicate to that place on the Earth. Yeah, so by keeping it at this certain distance, this certain point above the Earth constantly, it's really good for communication back to the Earth. Okay, but this geostationary satellite can only happen if it's going at the same period of the Earth. Okay, so let's move on to the next part of the content, which is redshift. So redshift is this idea that helps us to understand whether a star is moving towards us or away from us. Now, it is a little bit of a complicated concept. How it goes is that light waves are stretched out if a star is moving away. Okay, so light waves that we get kind of in the laboratory, that we pick up in the laboratory, if they're stretched out, if light waves from the star that we're observing are stretched out, then we know that the star is moving away from us. Okay, so for an example, if we had a wave like this and a wave like this, you can see that in the top diagram, the light waves are stretched out. They've got a really long wavelength, right? The wavelength is from here to here. So the light waves are stretched out, which means that the star is moving away from us. The wavelength is increased, and because the wavelength is increased, we have redshift. So our waves, our light, shifts to the red side. So you may already know that we have a spectrum of light which starts with red, then goes to orange and yellow, and green, and so on. Now, what this means is this is our spectrum of light, okay? Now, on the left-hand side, where red is, we have a long wavelength of light. And on the right-hand side, we have a short wavelength of light. So red is the longest wavelength. And purple is our shortest wavelength. Okay. Now, what this means is for a wavelength that is getting longer, so if we're increasing the wavelength, it must be shifting to the red side. Okay, if the wavelength is getting longer, it's shifting towards the red side because red has the longest wavelength. And it's the exact same for the opposite scenario. So if light waves are squashed together, as we see in this diagram here, the star is moving towards us. The wavelength is now reduced, so you can see that it goes from a wavelength of this distance to a much shorter wavelength. And if the wavelength gets shorter, we call it a blue shift. And that is because it moves towards the blue side of the spectrum. The wavelengths get shorter and it shifts towards the blue side of the spectrum. Therefore, we call it blue shift. Okay, so if it's redshift, it goes to the left, to the red side of the spectrum. If it's blue shift, it goes to the right, to the blue side of the spectrum, because the wavelengths are either getting longer or shorter, depending on whether the light waves are stretched out or squished together. So redshift is this really useful way of picking up light and understanding whether the light tells us that the star is moving away or towards us. Now, light from a star does not contain all the wavelengths of the electromagnetic spectrum. So it's not going to have all of microwaves, radio waves, infrared, visible, UV and gamma. It's only going to have a certain few of them. So it may have visible, infrared and UV, like our sun, and different stars give off different types of electromagnetic radiation. Now, elements in the star, so for example, hydrogen, helium, and oxygen, absorb some of the emitted wavelengths. And when they do, dark lines are present when the spectrum is analysed. And different elements produce different patterns of dark lines. And therefore we can know, well, what elements are in our lines. So here's a diagram to make a little bit more sense. A laboratory source of light produces this spectrum, okay? And it produces these dark lines to show which wavelengths are being absorbed. The pattern shifts, so the dark lines where they are shift, and therefore it's a redshift, right? We can see them shifting towards the red end of the spectrum, therefore we call it a redshift. So where these dark lines are present can also help us to understand how redshift is happening. The dark lines are there because of the absorption of the light in the source. Okay, so the position of the lines allows us to understand whether it's being shifted towards the blue end of the spectrum or the red end of the spectrum. Now, the bigger the shift, the more the waves are squashed or stretched. And the faster the star is moving, the bigger the shift. So the faster the star moves away or towards us, the bigger the shift or the squash. And then the more the waves are squashed or stretched. Okay, so going on to talk about our expanding universe. So Hubble was this astronomer a couple of centuries ago who found that light from distant galaxies was being redshifted. Okay, so light from the galaxies on the outer edge of our universe was being redshifted. He picked that up in his laboratory and he saw that light was being redshifted. Now we know that if light is being redshifted, it is moving away from us. Okay, so if light is being redshifted, the object is moving away from us. And therefore he could tell that the galaxies were moving away from us on Earth. And he also found that the further the galaxy was away, the more it was being redshifted. So therefore he was able to conclude that because the distant galaxies are constantly moving away from the Earth, the whole universe must be expanding. Okay, so it's not just specific to the Earth, it was being redshifted in relation to Mars, Mercury. All the galaxies saw that all the other galaxies, which were on the outer edge of the universe, were being redshifted. And therefore we could conclude that the universe is expanding. It's expanding very, very slowly, but it's expanding. So let's go on to talk about the kind of beginnings of the universe. We talked about the future and how it's going to constantly expand, but let's go back to the beginnings of the universe. So we talked about the Big Bang Theory. Okay, so the Big Bang Theory, I'm sure you all know, is this kind of idea that scientists have come up with to kind of think about how the universe started. And it's this theory, it's not been completely proven yet, but it is a very, very strong theory, which says that the universe expanded after exploding suddenly from a small, hot, dense region. So all started at this single point, this very small, very hot, very dense single point. All matter started from this tiny little point, which exploded and created our universe. This explosion sent matter outwards all around our universe. Okay, so this explosion sent the matter flying and just so happened to create our universe. Now, okay, we know that there was a sudden explosion, but scientists have said that, okay, if there was a sudden explosion, then high energy electromagnetic radiation would have been produced very soon after. Okay, so if we had a big, big explosion, lots of energy would have been created from that. But that energy kind of needs somewhere to go. So we produce all this matter, but we know that there must be some energy in the form of electromagnetic radiation. And this energy comes in the form of gamma ray high energy. Okay, so we have this high energy from gamma rays all around our Earth, which has been picked up by scientists and cannot be explained. It's this kind of background radiation that is constantly there and can't be explained. The only way to explain it is by saying that the only way to explain it is by saying that this must have come from the Big Bang. So we have this radiation which scientists have picked up and can't explain. So it's called cosmic microwave background radiation. Okay, cosmic microwave background radiation. And its existence gives evidence to the fact that we may have had a Big Bang. Okay, so I'll just explain it again. The Big Bang is this idea that we had a sudden explosion from a very small, dense region. This sudden explosion spat out matter all around the universe and created our universe. However, if this explosion did happen, then some high energy electromagnetic radiation would have been produced very soon after. And this radiation is now what we call cosmic microwave background radiation, and we have proved the existence of it. It's this constant gamma radiation all around us, which is background radiation. So, okay, we know that radiation can be dangerous, but we have it all around us. If you're saying that cosmic microwave background radiation is all around us, why aren't we kind of all in danger? Well, cosmic microwave background radiation is very small. It's a very, very small amount of energy which constantly kind of surrounds our Earth. So although we can't be in danger from it, we know that it is there. So let's talk about the future of the universe. The future of the universe, will it expand forever? Well, we don't know. Okay, we don't know whether the universe will expand forever and ever. It really depends on the density of the universe. So how kind of packed is the universe? How many stars do we have? How many galaxies do we have? Because right now, the stars in a galaxy only account for a very, very small percentage of our galaxies. So for example, in our galaxy, our solar system and the other stars in our galaxy only account for a very small percentage. And the reason that we know this is because our galaxies would spin much, much faster if there were only stars. So that must mean that there is some hidden mass, some unseen missing mass, which makes our galaxies spin slower. Okay, so if it was only stars, if it was only our solar system, if it was only all the other stars, our galaxy should be spinning much faster, but they're not. Our galaxies spin much slower than we expect. And because they spin much slower than we expect, there must be some mass making it move slower, some hidden mass. We can't see it, we don't know where it's coming from, but we know that it's there. And this is what scientists call dark matter. Okay, the reason it's called dark matter is because we can't see it, but we call it matter because we know it's there. And nobody knows where dark matter comes from. We don't know why. We know why it's there, but we don't know in what form. So dark matter, as scientists have predicted, accounts for 27% of the universe. So a good third of our universe is dark matter. It's this matter that we can't see, but we know must be there from our calculations. It makes the density of the universe much higher. So if there is dark matter which exists, our density of our universe would be much higher. Now it's really up to this dark matter to decide whether our universe is going to keep expanding or whether it's going to go the other way. If the density of the Earth, because of this dark matter, is smaller than a certain amount, the universe will expand forever. But if the density of the Earth and of the universe is bigger than a certain amount, the universe will stop expanding and will reverse. Okay, so it really is dependent on the density of the universe. If it's smaller than a certain amount, our universe will expand forever, which we call the big yawn. If it's bigger than a certain amount, the universe will stop expanding and will reverse, so it will start shrinking. This is called the big crunch. So it is all dependent on this idea of density. Okay, so that is the end of all of our content for today. I'm going to answer a few questions before we move on. Okay, so if the Earth was created by a single hot, dense point, where did that point come from? The answer is we don't know. As scientists, we have no idea where that single point came from. We kind of just say that they were there. Those elements were there, and that's just how it all started. That dense region just already existed, but we don't know how it came about. Where does cosmic microwave background radiation come from? So CMBR comes from the Big Bang. So when the Big Bang happened, it released loads of radiation, which is called cosmic microwave background radiation, which is still in the Earth today. Is light absorbed by photons? Light is not absorbed by photons per se. Light is photons. So don't worry if you don't know what photons is, guys. Photons comes in more at A level, but photons are this kind of particle version of light. So right now we know light is a wave, but light can also be a particle. And when it's a particle, we call it a photon. Okay, so let's go through some example questions. So what is redshift? What is redshift? Is it the time when a star moves from the main sequence to be a red giant? Is it the red filter used by astronomers to analyze the light from distant stars? Or is it the increase in wavelength of light from a distant galaxy moving away from the Earth? And how many galaxies show a red shift? Okay, so redshift is the increase in the wavelength of light from a distant galaxy. So if we go back to this page here, we see that redshift is this increase in wavelength, which means that light waves are stretched out, and we know that the galaxies move away from the Earth. How many galaxies show a redshift? Nearly all galaxies show a redshift. Okay, all galaxies around us show a redshift, and that's how we know that the universe expands. Okay, what does a larger redshift indicate? The galaxy has more stars, the galaxy is moving away faster, or the star is about to explode in a supernova. So a larger redshift indicates that the galaxy moves away faster. The redshift is larger, the wavelengths are more increased, more stretched out, so we know that the galaxy must move faster away from us. More distant galaxies show more redshift. Which major theory does this support? So this evidence supports the Big Bang theory. What is the basic idea of the Big Bang theory? The universe expanded from a single tiny point starting about 13.8 billion years ago. The universe will end in a giant dark energy explosion, or the solar system began when a protostar started nuclear fusion reactions. Okay, so the basic idea of the Big Bang theory is A, it expanded from a single tiny point starting about 13.8 billion years ago. What feature is believed to be the thinly spread remains of energy released in the Big Bang? That is cosmic microwave background radiation. Why do scientists believe in the Big Bang theory? And what percentage of the universe is thought to be dark matter? Okay, so why do scientists believe in the Big Bang theory? That is because it's supported by observation. Scientists only believe theories which agree with experimental observation. Even if a theory was the first scientific idea, it doesn't matter. It has to be supported by observations and evidence. What percentage of the universe is thought to be dark matter? That is 27%. Okay, so let's move on to some exam questions. So in 1929, the astronomer Edwin Hubble observed that the light from galaxies moving away from the Earth had longer wavelengths than expected. What name is given to this effect? So because the wavelengths are getting longer, what does that mean? What is the name for this effect? So the name for this effect of galaxies moving away from the Earth is redshift. And it was all proven by Hubble. Okay, so from his observations, Hubble was able to calculate the speed of a galaxy and the distance of the galaxy from the Earth. This shows the results of Hubble's calculations. So this graph here plots the speed of the galaxy moving away from the Earth and the distance in kilometers. So what relationship between the speed of a galaxy and the distance away is suggested by Hubble's results? So what kind of relationship do we have between the speed of the galaxy and the distance away from the Earth? So think about what kind of correlation the graph shows. Is it a positive one? Is it a negative one? Is it a strong one? Is it a weak one? So because we have this positive, although weak correlation, we can say that the relationship between the speed of a galaxy and the distance is that the faster the galaxy moves away, the further away it is. Okay, now the observations made by Hubble support the idea that the universe is constantly expanding. Now this means that galaxies are constantly moving away from each other and from the Earth. Okay, everything is getting further and further apart. So a student used this idea of a balloon, so blowing up a balloon with kind of dots on it, to model the idea of an expanding universe. So as he blew up the balloon, the galaxies were getting further away. So what is the strength in the student using this kind of model, and what is a weakness, do we think? So first of all, what do we think might be a strength of the student using this idea of a balloon to help him understand that the universe is constantly expanding? So a few minutes to have a think about that. What would be a strength of him using this idea of blowing up a balloon to show that the galaxies, to show the movement of the galaxies? And what would be a weakness of him using this balloon? Okay, very well done to Chess, who's got the answer spot on, and also Emma. So the strength of this model would be that the balloon shows that the galaxies do get further apart. Okay, that was the strength. So his model is good in that sense, but it's limited. And the reason that it's limited is because of two reasons. So you could have one of these two weaknesses. Either that there would be galaxies inside of the balloon as well as outside of the balloon. So galaxies should not only be represented on the surface, but also within the balloon. Okay, so the student has only drawn galaxies on the outside of the balloon, not on the inside. But in real life, there would be galaxies on the inside as well as the outside. Another thing you could have said is the balloon will eventually pop. And therefore, there will be a limit to how much the galaxy can expand. Okay, in the 1950s, there were two main theories to explain how the universe began. Now, the first one says that the universe has always existed. It is continually expanding. New galaxies are formed as older galaxies die out. Theory 2 says that the universe began from a very small region that was extremely hot and dense. The universe is expanding ever since. So theory 2 we know as the Big Bang theory. But in what way did the observations made by Hubble support both theory 1 and theory 2? So first of all, what observations did Hubble make? And secondly, how did those observations become evidence for these theories? So, in what way do the observations made by Hubble support theory 1 and theory 2? Well, both theories suggest that the universe is expanding, and that is exactly what Hubble observed. He saw the redshift of the distant galaxies, and he said that, okay, the galaxy must be expanding. And these two theories both say that that the universe is constantly expanding. But now, most scientists believe that theory 2, otherwise known as the Big Bang, is correct. So what do you think might have led scientists to start thinking that theory 1 is wrong? So why do you think they started to believe theory 2 more than theory 1? What might have happened? What might have happened for scientists to believe theory 2 over theory 1? Okay, so what is likely to have happened, and what did happen, is that new evidence was provided. Okay, so new evidence, such as cosmic microwave background radiation, may have come into light and made scientists stop kind of believing theory one. So the new evidence was provided and could not explain theory one. Okay, so an example of this new evidence is cosmic microwave background radiation. So when cosmic microwave background radiation was discovered, people started to stop believing theory one. And theory one says that the universe has always existed. Well, if the universe has always existed, then there should be no explanation for cosmic microwave background radiation. Remember, it's the creation of the universe. It's this explosion to create the universe which created CMBR. But we know, okay, we've proved the existence of CMBR, but if the universe has always existed, then CMBR should not be there. So new evidence has come into light and cannot explain theory one. Okay, so we'll just go through this last question quickly. So when observed from the Earth, there is an increase in the wavelength of light from distant galaxies. Explain how this observation supports the Big Bang theory of the formation of the universe. So this would be a 4-mark question in an exam and is very, very common. So the way that you would answer it is the furthest galaxies show the biggest redshift. Okay, so the furthest galaxies show the biggest redshift, and therefore the furthest galaxies move the fastest. Remember, the faster the galaxy moves, the further away it is. So the universe must be expanding. And if the universe is constantly expanding, it must have started from a single point. And that's how to answer that 4-mark question. So we'll end our webinar there. And tomorrow we're going to go over a recap of space and start our new topic, which is atomic structure.
Brilliant. Thank you, Preshayla, and thanks everyone for attending today and getting involved in all of the activities that Preshayla set out for you. If you want to join us for any other tutorials today, we have Foundation Maths at 11, then Chemistry at 2 and Biology at 3. Otherwise, see you in our next physics session tomorrow morning, and have a lovely rest of your day. Bye.
Thank you. Bye.